Now we'll look for keypoint descriptor. As each keypoint has location, scale, and orientation, now the next step is to compute a descriptor for a local image region about each keypoint, which is highly distinctive and as invariant as possible to variations such as changes in viewpoint and illumination. We're going to build a feature vector of, uh, of some length based on the property of histogram of gradient. The key point, which is further divided into 16 blocks of 4 by 4. Here we can see, here what we do is we build a feature vector and it will have some length and it's based on the histogram of gradient. And in order to do this, we take a 16 by 16 window around the key point. We can see here a key point with the red dot, and we take a 16 by 16 window around the key point, and which is further divided into 16 subblocks of 4 by 4 sides. Now for each subblock, 8 bins, 8 bin orientation histogram is created. You can see, like for each of this block, we create the histogram of orientation, and for 4 by 4 descriptor over 16 by 16 sample, array are used in practice, which is 4 by 4 by 8 directions, and that gives us 128 bin values. Now it's represented as a feature vector to form a key point descriptor, or we will have 128 numbers of a feature vector which is going to be used to describe a single key point. And once we have all 128 numbers, we normalize them, and we can say the key point is uniquely identified by this feature vector. And as we have seen that the orientation are placed into the 8 bin histogram, orientation in the range of 0 to 44 degrees are added in the first bin, and 45 to 89 add to the next bin, and so on. And the amount added depend on the magnitude of the gradient. And we can see here that unlike the past, the amount added also depend on the distance from the key point. So gradients that are far away from the key point will add smaller value to the histogram. This is done by using a Gaussian weighting function. We have got this Gaussian weighting function, and we multiply this with this descriptor. And what we do is this function simply generates a gradient, and we multiply it with the magnitude of the orientation, and we get the this weighted gradients or weighted orientation. Here what happens is, like the farther away the magnitude gets lesser, like the lesser the magnitude will be, like the key point, the center key point, any orientation that is near to the center will have a bigger magnitude, and the farther orientations will have the less magnitude. That means we get some kind of weighted orientations here. And after the generation of key point descriptor, we will evaluate the shift descriptors. And for the evaluation of shift descriptor, the database images were subjected to rotation, scaling, affine stretch, brightness, and contrast changes, and noise were also added before evaluating the shift descriptor. And feature point detectors and descriptors were compared before and after the distortion. And here is the evaluation of the descriptor. And here the first graph, we can see that for the evaluation of error, a measure is, like the error measure is the correct mere descriptor percentage, we can see here the correct uh, in vertical direction, and how often, this means how often one match is the best, the corner one, the correct one. And for the evaluation, in the experiment, the author varied a couple of things. The first thing that is the easiest to see here is in the number in the horizontal directions here, that this gives the width of the descriptor, like the angle, and uh, this is the number of those of the histogram that got used. And we saw that using 4 by 4 here, using 4 by here, the number of descriptor here at 4, at here 4 by 4 here we see it gives the maximum result, and so it looks like 4 by 4 was good thing to use. As we can see here, this 4 gives us the good result. And other thing shown here is how many orientations in the histogram, or how many bins were used. We can see with 4, 8 or 16 here, like with 4 orientation, with 8 orientation, and with 16 orientation. And what we found here is that we can see 8 gives better than 4, however 16 doesn't give better than 8, so 8 was picked. Like we can see here in the graph, this uh, this 4 gives us the result, but it's not that good as 8 orientations. And if we compare 8 orientations with 16s, there is no big difference between these two. So the 8 was picked. And let us see the results in the picture. Here is the original image in the left side, and uh, drawn, and we can see image and the drawn on the top of the picture. There are lots of feature points, and they took the picture and rotated it in 15 degree. They scaled it down to 90 degree and 90%, and the stretch is to 10%, and they changed the brightness and the contrast. Here we can see this is the transformed image, and they took a look at the feature points, and then they tried to match, and what they found is they found like 78% of the points, interest points, were matched. So after the transformation of the original image, they found 78% of the match. And here is another example. It's also taken from the paper of David Lowe, that's SIFT paper. Uh, what what are looking for is that the sub images in the left side. We can see the sub images on the left side, and we were looking for the patches over here. And what we gonna see is we're gonna create a little shift features on these things here, on these images, and we're gonna look for those patches in the corresponding image. And what we find is here, and these features are these patches are found here in these images. That means we can find the perfect match. We can find the perfect match in the right images from these shift descriptors. So we can see there we can get the perfect match in the right images. So it's all about shift detector. And here what we have studied is like how the feature detectors, how we can create a feature detector, and how that can be used to match the images, like how we can use that feature editor to match two different images.